Hi, it's time for another math easy solution. Turn to discuss further into approximate integration and look at accuracy and error bounds or boundaries. Basically, in my previous video, I went over using the trapezoidal and midpoint rules of approximation for n equals 5 to approximate the following integral. This one from integral from 1 to 2 of 1 over x dx. And then I also showed if you solve this, this becomes ln 2, and this is, if you plug in the calculator, 0.693147, and it keeps going on and on. And now to recap of my last video, basically the results of the approximations as well as their visual representations are shown below here. So this was the trapezoidal rule on the left side. As you can see, there's 5 trapezoids, and in the right side there is 5 rectangles that use the midpoint rule. So these are trapezoids, midpoints. Now visually the trapezoids appears to be more accurate than this because you could see some empty spaces here, but it makes up for it by this addition space there. And in fact that's more accurate. Basically, to recap, the approximation we got from T5 or the trapezoidal rule was 0.695635, which is bigger than this 0.693147, and the corresponding error when you subtract ln 2 minus the approximation, we get about negative 0.002488, and then the right side, as you can see, the approximation using midpoint rule was 0.691908. And then the error, corresponding error, ln 2 minus this, that's just a difference, which is the error, 0.001239, which is about half of this in terms of the absolute value. So the midpoint rule was more accurate, even though this one appears to be more accurate. And I'll explain that in a bit. Basically, the results show that the midpoint rule is about 2 times more accurate and has an opposite sign compared to the trapezoidal rule, even though at first glance visually the trapezoidal rule appears more accurate. I'll explain this in detail later in this video, but first we can extend the calculations to compare the approximations for, well, n equals 5, 10, 20, and for all 4 approximation methods, left, right, trapezoidal, and midpoint rules. And you can learn more about these in my earlier video on approximation. So here's an Excel sheet that I have made. There's a link to it in the description below as well. You could go and view it. But if we click edit, so this pops up right here. So that is this is the Excel file I made. So for a equals 1, b equals 2, these are just the boundary, the limits of the integral, and fx equals 1 over x. For n over 5, we get delta x. Basically in this, I just solve for, well, xi minus 1, xi, and xi middle. And then I find the corresponding f of x functions, fxi minus 1, and then the right endpoint and middle endpoint. And then from this I was able to, well, sum these up and multiply by, well, delta x. And then we get, these are the errors for this, and the trapezoid again is the average of the right two. Yeah, and basically here, if I click it, so basically this is just averaging the left and right there. And also for n equals 2, as you can see, you just make a bunch more rows, and then our delta x becomes smaller and smaller. And then for 20, we get this, and then basically here's a summary of all of them. Approximation of the integral from 1 to 2 of fx equals 1 over x. And basically the corresponding errors are all shown here as well. And basically I've copied and pasted this here. Don't save. So what we get is right here. Here's all the data. You can go and review it in detail later. You can do that on your own. And here's a summary. As you can see from this, the approximations gets closer and closer to the exact 0.69314 as they keep going down and down. So as you can see, this one is the closest so far, the middle point. And the corresponding error values, as you can see here, here's these the values here, and this is again the most accurate. And then these are both way more accurate than the left and right endpoints. So now we can make several observations from these tables, and here's the observations. Observation 1, in all methods we get more accurate approximations when we increase the value of n. But important note is, but for very large values of n results in so many arithmetic operations, as you're just adding a bunch of them, that we have to beware of accumulated round-off error. And again, this depends on the computing power of the computer calculator that you are using. So yeah, the bigger the number of n, you got to make sure you have a computer that can handle it. And now the errors in the left and right endpoint approximations are opposite in sign, so which makes sense, because literally they are just the left and right endpoints. If from the left side you get a negative error or smaller than the actual one, the right side is going to be bigger. That's just that's usually what happens. So they're opposite in sign and appear to decrease by a factor of 2 when you double the value of n. So if you go if you go times this by 2, as you can see, this, yeah, when you double it here, you get this part right here. This is like 0.05, 0.02, and then divided by 2 again. This is, yeah, this is basically we're dividing by 2. We get to here, divide by 2, and we get over here. So basically these are going smaller and smaller by 2 every time we double. And the trapezoidal midpoint rules are much more accurate than the endpoint approximation, and that you could easily see from the errors there. Now the errors in the trapezoidal and midpoint rules, this is interesting, they are opposite in sign and appear to decrease by a factor of 4. So instead of divide by 2 here, this is 12 goes to 3, and 3 goes to 32 goes to 7-ish, or like between 8-ish actually. This is so again, this is dividing by 4. So divide by 4 or divide by 4 as you go down here as well. 4 goes to 6, and then divide by 4, it goes to around 1.5-ish. I mean 0.00015-ish, etc. So it's going down by 4 when we double the value of n. And now the size of the error of the midpoint rule is about half the size of the trapezoidal rule. So as you can see, this this is 2.4, this is 1.2, this is 6, this is 3, this is 1.56, this is about this is about 7.8, which is half of the ET. So this one half of, well, absolute value of error t, which is in fact actually well, it turns out that these observations are true in most cases. Now the interesting part, like I showed in the graph above over here, this one, so the trapezoidal rule appears to be, well, more accurate. There's barely any empty spaces, one there, but there's barely any. But the midpoint is, well, it's it's double the accuracies. To see why we usually expect the midpoint rule to be more accurate than the trapezoidal rule, consider the following figure. Let's say we zoomed in one of these. Let's say we zoomed in one of these. So we zoom in this. So to do that, yeah, let's go in here. Yeah, so if we were to zoom in like that, let's draw it but really big like this. So this is at, all the way down, this is at, that's xi minus 1 is the left endpoint, this is at the right endpoint, and then right in the middle we have over here xi, and then with the overline line like that, just signifying it's the middle. So now let's draw the midpoint right here, the midpoint rectangle. So it goes across like this. Let's draw a dashed line. So this is our midpoint. Yeah, our midpoint approximation. I just fixed that up. So it looks something like this. So now let's say we, well, rotated this so that it's more on, yeah, it's more clear in how much error there is. So if we rotate it, because again, there's extra space here, but there's extra space to make it up for it. So delete this. Now let's rotate. So we would rotate down. So rotate right here. So we were rotating clockwise in this case, just so we have something that looks like this. We draw a straight line. I'll draw it like it'll be right on it. Let's draw it better. Let's draw a better line like this. Oops. Okay, and then draw it all the way up, straight line. So we've basically rotated this all the way to get here. So now we can see that the error is right here. because now it's the error from this part right there. Oops. Right, mark this up again. So now as you can see, the error is over there, and we'll call this in the red. This is the M or EM error right there. So that's the error, or the midpoint error. And now let's look at, well, the trapezoidal error. Well, we'll just draw the trapezoid. It's from the left endpoint, so it's an average. And then, like I showed, all you do is draw a straight line. So it's from the right endpoint, left endpoint, and the average is a trapezoid straight down like that. And again, and then it goes all the way down. So that's the only thing different. And then the error as well, right here, the difference from the f of x, the black line. And now there is our error, as you can see here. Yeah, what's interesting is, so we'll call this E of trapezoid. So as you can see, this error is actually much bigger. Yeah, it is much bigger. Now if you were to look, let's say, at half of this, draw this exactly like this half across. As you can see, and then just look at here, this is about two times the size of this. So this error is, yeah, it's about 2 times the size. So, and then there's obviously this other side there. So this looks roughly 1/2 ET. And again, use absolute value of it. The absolute value, I'll just use absolute values here because this one is, again, its opposite sign. So in this case, we have a negative right here, and this is positive there. So again, we could say that EM is roughly equal to negative 1/2 ET, because this is on the opposite side of this f of x function. And basically, thus from the above figure, yeah, it does in fact appear that the midpoint rule error is smaller than the trapezoidal rule by about 2 times, and again opposite in sign in most cases. Basically, when you rotate, it becomes really clear. And then this helps explain why we should expect the error to be smaller in most cases. And also the observations listed above, yeah, are basically listed above are backed up by the following error estimates, which I will prove in later videos the formulas for. So stay tuned for that. So basically, the error bounds, or the error bound estimates, the boundaries of them are right here. Suppose that the absolute value of the second derivative of f of x is less than or equal to k, for a is less than or equal to x, is less than or equal to b. Basically, what this means, if E and T and E and M are the errors in trapezoidal and midpoint rules, then we basically have, I'll write these formulas out, and again I'll prove these in later videos. So stay tuned for that. This becomes the error estimate. So this error of trapezoid absolute value is going to be less than k times b minus a power of 3 divided by 12n squared. And then for the midpoint, we got this is going to be, well, and again, these estimates, it's going to be the exact same thing as above one, but it's going to be, well, divided by 2. Actually, this is going to be 24n squared. So again, this equals to, I'll write this down actually like this. So this is less than or equal to 1/2 this absolute value of t. Yeah, of the trapezoid, which is right there. So just divide by 2, you get that there. So these are the formulas. I'll just leave this like that. And now this number k is basically can be any number larger than or equal to all values of the second derivative of f of x right here. But smaller values give better error bounds. So this could be just pretty much anything. It's just saying that it needs to be, when you're trying to see what the estimate is, yeah, k needs to be, well, greater than or equal to the f of x value, any f of x value that you're looking at. So it can't be less than it in the error estimate. So now, and again, it could be anything greater because, well, it's an estimate. This is a maximum estimate, so it just means that the error is going to be less than it. So you could, if you put a large value of k, it still holds true, but you want the smallest one possible. So yeah, and basically it can be. And now notice how the error bounds correspond with our observations. Observation 4 corresponds, we'll go back to observation 4, which is the errors in a trapezoid midpoint rule are opposite in sign and appear to decrease by a factor of about 4 when you double n. So this is saying that it goes down by 4 when you double n for trapezoid and midpoint rules. and basically this corresponds to the n squared in the denominator of both equations above, because when you double the value of n to 2n, the error decreases by 4, otherwise written as, well, n squared. If you had, because of this n squared, you have, whenever this doubles, 2n squared is 4n, so it's 4 times the previous error there. I mean, 4 times smaller because you're dividing by it. And now observation 5 corresponds to the equation of the midpoint error bound being half of the trapezoidal error bound. And that's where I stated it's half of it. So midpoint rule is about half, and yeah, I'll just write it down right here. Half absolute value of ET. Yeah, so that's the observation, this one. And now the fact that the error bound estimates correspond to the second derivative f prime of x is not surprising, because if you look at the figure above illustrating the trapezoidal and midpoint errors, yeah, because when you look at them right here, the more it curves, basically, the bigger the curve, for example, was something like this or something like this, you're going to have bigger errors. And those correspond basically right here, because the second derivative measures how much the graph is curved. The more curved, the larger value of k, the bigger the f double prime of x, and the bigger error estimate you should be estimating. And also recall from earlier videos on graphing, the second derivative measures, well, how fast the slope of y equals fx is changing. So it's like an acceleration versus velocity versus the distance, etc. And you can learn more about this graphing stuff in my earlier videos as well on graphing. So now let's just do a quick example. Let's apply the error estimate to the trapezoidal approximation in example 1. So we have f of x equals to 1 over x, which you could write this as x to negative 1. Now the first derivative is, well, put the negative 1 down, x negative 2, which is equals to 1 over x squared. Now apply the second derivative of this, putting this negative 2 down, you'll have a positive 2, and then, well, this is going to be times x minus 3, which equals to 2x cubed. So what this means is that we have to pick k, which is greater than or equal to x over 3, but now since we're dealing with, well, the limits from x is less than equal to 2, greater than equal to 1, the larger, if you put number 2 in there, it gets smaller, so the biggest one we could put is put 1 inside. So k has to be greater than equal to 2 over, well, 1 cubed, which equals to 2. So we have to put minimum 2, so let's just choose k equals to 2 because that's the smallest, and that'll give us the smallest, most accurate error estimate. And again, this 1 is equal to a equals 1, that's the b equals to 2, and now we could apply the error estimate. So in this case, ET is less than or equal to kb minus a cubed over 12n squared, using trapezoid rule, and again this equals to 2 times 2 minus 1 cubed over 12, and this is a 5. So n equals to 5 from our example above. And then this is squared, so what we get here, this is just 1, so it's going to be less than equal to, bring it down here, this is going to be 1 over 6, that's 1, and then 5 is 25. This equals to 150, and now plug this into the calculator. If you plug this in, it's roughly equal to 0.00666, keeps going on and on, let's put a 7 to round up. So that is our error estimate. So the trapezoidal rule, the absolute value of the error is less than 0.006667. But now if we compare this error estimate to the actual error right here, which we calculated was ET is roughly equal to negative 0.002488, and that's, well, that's shown in the summary above here. That's for n equals 5, as well as, well, last video, and we have it over here. That's just showing where I got that number from. As you see, this is about, well, 3 times less, but again, it's still less than it. So this actual one is less than this right here, which is what we want, or put less than equal to. So this holds true. And also I just want to state, thus it can happen that the actual error is substantially less than the upper bound given in the error bound estimate formula. So just saying sometimes the actual error is still much less, in this case 3 times, than the estimate over there. Anyways, that's all for today. Hopefully you learned from this pretty extensive video on error bounds and accuracy on the trapezoid midpoint rule and in approximations in general. Anyways, thanks for watching. Like always, you can download these exact notes in the link below, and stay tuned for another math easy solution.